Okay, so let's start off by looking at some nuclei. So first of all, I've got lithium-7. I want to know how many neutrons and how many protons it has. So what I need to do is look at the periodic table. So let me go over to periodic table, and you can see lithium has an atomic number of 3, so that's the number of protons that it has. So lithium has 3 protons, and the number of neutrons it has is this number up here, 7 minus the number of protons, so that's 4. So remember, we might write this as lithium 4, 7, where this lower number we call Z is the number of protons, and the top number, which is A, is the number of protons plus the number of neutrons. All right, let's do the next one. So the next one is chlorine 36. So again, pop over to the periodic table. And if we look at the periodic table, it's way over on the side over here. It's got atomic number of 17. So if we go back here, it's got 17 protons. And so the number of neutrons is 36 minus 17, which is 19 neutrons. All right, and then same thing for radium. So we've got radium 224. So let's go over to the periodic table. Look at radium. Radium is way down near the bottom. Okay, so where's radium? Radium is over on the left side near the bottom. It's got an atomic number of 88, so it's got 88 protons. And so it's got how many neutrons? 224 minus 88, which is 136 neutrons. So you can see as we go up in the periodic table, the bigger the number of protons, the bigger the number of neutrons. In fact, the neutron number becomes way bigger than the proton number as we go up in order for the nucleus to remain stable. Okay, let's do some binding energy calculations. So I'm told the masses of the stable isotopes of silicon are as given in atomic units. I want to calculate the binding energy for each nuclide. Okay, so remember 1U in atomic mass units is 1.66 times 10 to the minus 27 kilograms. And we use the conversion factor that's 931.5 MeV per c squared. And you'll see in a minute how that works. We also need to know what the mass of the proton and what the mass of the neutron are in U. So for a proton, it's 1.007267, and we keep a whole bunch of significant figures when we do this, because often the differences are very small fractions of an atomic unit, and so if you round off, you're going to get the wrong number. All right, so we need to calculate the mass of the neutrons plus the mass of the protons for each one. And then we need to subtract that from the mass, subtract the mass of the stable nucleus from it. So we do mass of the protons plus the mass of the neutrons minus the mass of the isotope. So that's going to be my delta M, and my binding energy is delta M times c squared by Einstein's equation, E equals mc squared. All right, so let's do this for these different isotopes. I've got 28 silicon. So silicon 28, silicon 29, and silicon 30. So silicon, if we look at up in the periodic table, silicon is over right over here. It's got 14 protons. So silicon has 14 protons. So if I do for silicon 28, it's going to have 14 protons and 14 neutrons. So the mass of the neutrons plus the protons is going to have 14 times P plus 14 neutrons. So that's 14 times 1.007267 U plus 14 times 1.008665 U, and I get 28.223048 U. Okay, so that's the mass of the pieces that make up the nucleus. The mass of the nucleus itself is given by this number that I've just circled in red. So delta M is going to be that, the mass of the constituents, minus 27.976928. Oops, I need to put my symbol for U in there. Okay, so I get 0.24612 U. That's my delta M. So delta E is equal to delta M times C squared. So that's 0.24612 U. And now we do our little trick. We put in our conversion factor, 931.5 MeV per C squared. So now when I multiply by C squared, because remember I have to have delta M times C squared, those C squareds cancel. So I never actually have to put in my number of 3 times 10 to the 8 for C. So I get 229.3 mega electron volts. So that's million electron volts. So that's my binding energy. Okay, so the nucleus itself weighs less than the constituent parts, and so that gives it a lower energy than the constituent parts, and so that means that it's a more favorable state for the nucleus to be in. Okay, let's do the next one. So now I've got silicon 29, and what the difference is now it still has 14 protons because it's silicon, but now it's got 1 extra neutron in there, so it's going to be slightly heavier. So let's go ahead, put in proton mass and the neutron mass. So now I get 29.231713 U. And the mass of the nucleus, I'll do it in blue this time. So the mass of that isotope is that, so I need to subtract them. So my delta M is equal to 29.231713 U minus 28.97649 U, 496 U, and I get 0.255217 U. So again, don't round these off. So delta E is going to be 0.255217 U, and multiply by 931.5, and I get 237.7 mega electron volts. Okay, finally let's do it for silicon 30. So silicon 30 has 14 protons and 16 neutrons. So it's 14 times 1.007267 plus 16 times 1.008665 U, and I get 30.240378 U. Then I go up and I look at my problem, find the mass of the nucleus when it's all put together, and subtract it. So delta M is 30.240378 U minus 29.973772 U, which is 0.266606 U. So delta E, the binding energy, is 0.266606 times 931.5. So I get 248.3 million electron volts. Okay, so it's a pretty straightforward calculation. Just make sure never round off your numbers until you get to the very end of the problem.